right, everybody. Thank you for coming. This will be actually our last colloquium for the semester. And so we will reconvene next semester, of course. And today we have, as you can see, and as you have read, our own professor of mathematics, Stephen Casey. He is also an affiliate professor of computer science at our university. He served as a chair in our department 2017-2019, and he has been a visiting research scholar at the University of Maryland. So what is his research about? His research is in complex analysis, harmonic analysis, and number theory with applications to signal and image processing. His work includes multi-channel deconvolution and multi-rate sampling, sampling in Euclidean and non-Euclidean geometries, sampling for wideband signals, signal adaptive frame theory, and the analysis of pulse-train signals. So he has published 60 articles, I'm sure more than that, Steve. I think being modest with 60, edited one book and is working on a second book. He has given over 100 talks at various universities in Europe, Asia, and North America, and his research has been funded by 24 research grants and 4 contracts. He has received several awards from AU for teaching, including University Faculty Award for Outstanding Teaching and the selection by our students for Outstanding Teaching. Also received in 2019 Drew University Alumni Achievement Award in Sciences. And to add to all of that, he was awarded 2 provisional patents and 2 full patents for his work in signal adaptive processing, and is filing right now for with American University. He is filing right now for a 5th patent. And today we will hear about a lot of mathematical gadgets. And so, Steve, stage is yours, and let's welcome Steve Casey, and let's hear about cool math.
Well, excellent. Thank you very much, Julia, for that fantastic introduction. Today, I am proud to say that I don't have to worry about announcing something that my patent lawyer was going to yell at me about, because this is mathematics, and I don't think I could get a patent out of this, although the multi-channel deconvolution stuff is really interesting, but unfortunately, that's been out for sufficiently long. The new stuff on sampling is, well, there's one machine, but it's a mathematical machine, and so I don't know how one would turn that into a chip for your phone to use. But with that, let me start sharing screen, and we should all be looking at this presentation. And so let me go to full screen mode, and we should all now be seeing, at least according to my green button. So today's talk is got a very interesting title: Analytic Bezout Equations and Sampling in Regular and Radial Coordinates. A couple of weeks ago, I was a invited speaker at the AMS Western Sectional Meeting, and it was in a session on harmonic analysis, geometry, frames, and sampling. This talk is a lengthened version, so that hopefully it's accessible for the students of that talk, and it shows the sort of mathematical thinking, hopefully for our students, that goes into a lot of my research. So, talk comes in 4 parts: preliminary definitions, sampling, this idea of multi-channel deconvolution. But of course, every great talk, or many great talks, should include number theory. And I'll, of course, give my shout out, if you will, to number theory, because a lot of the language and the way that I approached these problems was inspired by number theory. And that led to deconvolution algorithms. And then finally, how this all ties together via Cauchy theory, Jacobi interpolation, and how one can create a virtual plethora of sampling formulas. All right. Again, for the students, what we say a function f is called absolutely integral, and this is the integral here is in the sense of the Lebesgue integral, but you can think Riemann or Riemann Darboux. If the integral of the absolute value of f is, and that's the norm, the L1 norm of f is less than infinity. If f is an L1, we say f1 is the L1 norm of f. Similarly, a function is called square integrable, f element L2. If the absolute value is squared, the integral of that is a bounded number, and this again is called the L2 norm. The beautiful thing about L2 is that it's a generalization of linear algebra. It's kind of an infinite dimensional generalization of what we learn in linear algebra. There's things like basis elements, and you can expand things in these basis elements, and you can talk about things like orthonormality in your functions. Well, a great example of this goes back to Fourier, who gave us what we call Fourier series. And this has to do with the functions that are L2 on a region, or better way to think about it is functions which are periodic with period, say, 2 phi here. And then what we do is we just take one snapshot, namely in that interval 2 phi, and these are L2 functions. Here is that snapshot. And what we can do is we can think of these functions as having an orthonormal basis. Now, that orthonormal basis can be written down as e to the I pi nt divided by phi. And so this representation here is the inner product, if you will, of the function with one of those basis elements. And that then is going to give you your coefficient, which represents the function in terms of that basis. And if these coefficients are absolutely summable, then we can synthesize, we can recreate the function by gluing everything back together in a series. So there's two fundamental operations in harmonic analysis. The first is analysis, to take your element and break it down into the components and find out what is the coefficient or representation of a given component relative to this basis element, and then synthesis. From those coefficients, rebuild the function. And another definition I want to give is a trick called the periodization, and this is especially true with a windowed snapshot. If I have that, if g of t is a function such that its non-zero region, namely its support, is contained in 0t, then I can kind of concatenate this. Just basically take that snapshot of t and continue it. What does this look like? Well, here's a lovely function, the square function, the Haar wavelet, if you will. And here's a set of Fourier approximants of that function. The higher the number of the coefficients, the closer the approximation. Well, that's great if you're assuming a periodic function on a given window, but how do you analyze a function that may not have a periodic structure but goes over the entire line? Here, what we do is we relax the sort of discrete condition of the Fourier series, and we take what's called the Fourier transform. So just like we had analysis and synthesis from our previous discussion, we call the Fourier transform the integral over all of R, the function weighted with, again, this element, which looks like the same kind of element, but here it's a continuous element of the ON basis. And here we want to say that this is a representation, f of t is a representation of t in time, and omega f hat is its representation in infinity, in frequency space. And to boot, again, synthesis, this is analysis. Synthesis is taking the inverse transform, but that's simply given by this integral here. And if we set this up correctly, and we have, with the 2 pi upstairs, we have a beautiful relationship that the L2 information of f is preserved by the Fourier transform. There's no constants involved. It's just the L2 norm of f in time is equal to the L2 norm of f in frequency. And here's some of the kind of things that you would want to take a Fourier transform of. A cosine wave, well, here we want to think in terms of generalized functions, but what we have is actually a pair of Dirac deltas where the Dirac deltas are located at omega and negative omega, and the omega represents the frequency of the wave. A sinc function is very important because its transform is going to be the indicator function or the boxcar function or just chi of a region. The indicator function, the width of the indicator function is a function of these zeros over here. That's really important. The Gaussian. In every transform analysis, you have to compute the transform of the Gaussian. And the beauty of this is that the Fourier transform of the Gaussian is the Gaussian. And Dr. Nolan would like to, and I will share with him my notes, this leads to a gorgeous proof of the central limit theorem. This simple fact leads to beautiful proof that I give in my harmonic analysis class of the central limit theorem. And again, a shout out to Dr. Nolan and Dr. Gerard and Dr. Barone. The double exponential, its Fourier transform is, well, I call this the Cauchy distribution. Some people call it the Lorentzian, and this is an example, as Dr. Nolan would say, of a heavy tail distribution. So, what is convolution, and why is it useful? If I have two functions that are absolutely integrable, the convolution of f and g is defined by this operation here. It's denoted by f star g, and it's taking one of the functions, turning it backwards, and then sliding it across the other function and computing the integral. And so what you're doing is this operation is gleaning from the function the amount of information that you can get in a window. And you think, wow, this sounds interesting. Is it useful? Well, this is the model for what the engineers called LTI systems, linear translation invariant system. Every remote sensed signal, image signal, remotely sensed information is modeled by this equation. And as Dr. Nolan points out, and I saw this integral on his board the other day, I saw a convolution integral, and he was likely doing the sum of random variables is expressed as a convolution integral. It's extremely important throughout a lot of mathematics. Convolution is commutative. F star g equals g star f, and if f, g, and h are of compact support. So I do apologize. I've been using that term, and I thought about this right before the talk. The support of a function is the closure of the set on which the function is non-zero. And we say it's compactly supported if that closure is in fact a closed and bounded set, a la, the Heine-Borel theorem. And if f, g, and h are compactly supported, convolution is also associative. But what's really beautiful from the Fourier perspective is that the Fourier transform turns this mysterious property of convolution into just multiplication. But then in duality, it turns the process of multiplication into a convolution. Interesting. That's going to help us with the deconvolution. However, there is no function g such that f star g equals f for every f in f. We have to construct this function. Basically, we start out with, an interval, and we make sure that the characteristic function of that interval we normalize it so it has area 1. And what we do is we bring the support in gradually, but preserve the area. So you end up with an object which is infinitely tall and has integral 1. And such an object doesn't exist as a function, but it exists as a so-called generalized function. And you think, oh, great, another idea I have to learn. It's really quite simple. Generalized functions exist as in terms of their action on functions. And a great way to understand this, to wrap your head around it, is you can think of how can you tell it's a windy day if you're inside? Well, you look out the window and you look at the trees. The wind is making the trees move back and forth or bend, and yet you don't see the wind, but you know the action of the wind. So a distribution acts on a space of functions, producing a result. The granddaddy of all distributions was studied by the physicist Dirac, and it's called the Dirac delta, and it is the convolution identity. We'll see a picture of it in a little bit. Okay, if you get nothing else from this talk, you will learn how to use the word athwart in a sentence. Here I'm quoting wonderful mathematician Solomon Bachner. The Poisson summation formula and Cauchy's integral and residue formulas are two different aspects of a broad gauge duality formula which lies athwart most of analysis. Wow. What is this Poisson summation formula? And oh my goodness, is that thing from complex analysis, Cauchy integral formula? Well, let's see. And how could you ever use it to solve practical problems? Well, we all own cell phones, and we're happy that they work. I mean, mine right now is on silent, but it's gathering information from the outside world, keeping me up to date on my beloved Celtics, and making sure that, you know, the plans for Thanksgiving are going along smoothly. There is a theorem that says that if I have a function that f hat is, both f and f hat are L2, and the support of f hat is contained in a region negative omega omega, that's what we call a band-limited function. That means it doesn't oscillate too much in time, and that its Fourier transform is limited, is limited inside a compact region in frequency space. If you have that, then what you can do is do something remarkable. You can sample, so think of these Dirac deltas as samplers at a rate sigma, where sigma is less than 1 over 2 omega. 1 over 2 omega is called the Nyquist rate. Let the action of that go on the function f, and then from these discrete samples, do a convolution integral with, oh, wow, the Fourier transform of the characteristic function of an interval, the sinc function. And what you get out at the end is perfect recovery. And if sigma is less than 1 over 2 omega and f of n sigma is equal to 0 for all n and z, then f is identically equal to 0. So if you have two sample sets of two different functions and they agree, you sampled above Nyquist, and they agree at all those points, you've reconstructed the same function. A set omega, if I just throw down points, is a set of sampling and interpolation if there exist constants above and below. And for a couple of the experts in the room, you'll recognize this as the so-called frame bounds. But basically, they're bounds above and below that allow us to reconstruct the information, even if the sample points are not laid down via some uniform method. And in particular, the sampling sets, it previously used to have to be discrete. Namely, they had to be separated. You couldn't get points getting arbitrarily close. But the deconvolution work allows us to kind of transcend that. And then there's a very sophisticated tool called Bertolini-Landau densities that allow us to build these so-called sampling sets. Well, every good proof, like every good talk, Dr. Eniai would say, has to include a proof. Here is a really quick proof of the Shannon sampling formula. What I need is a Fourier transform computation, which I'm going to say is represented by the Poisson summation formula. Bachner said, hey, this is important, and we should listen to Bachner. If I take the Fourier transform in the generalized sense of a train of deltas sampling at rate sigma, then in the transform domain, that's a train of deltas sampling at the rate 1 over sigma. And a proof of the Shannon formula is quite beautiful. What I'm going to do is I'm going to take f hat of omega. It's band limited. I am then going to do the circ operation. I'm going to concatenate it. And then I'm going to do a cheap trick. The cheap trick is to then cut it off in one copy. Okay, Darcy, the first time you see a cheap trick in class, in analysis class, it is.
It's still a cheap trick the first time you see it.
And the second time you see it, it is a
Useful technique that you should apply.
a useful technique. Okay. See, I've got the students so that they understand the thinking here. Okay, so this is a cheap trick, but watch this. F out of omega is this concatenated function cutoff. But of course, if I write this out in terms of deltas, that's the train of deltas sampling at rate n over sigma. And that's the convolution of that train of deltas with f hat times chi of negative 1 over sigma, 1 over sigma. That's some kind of a sinc function. But look, here's your proof. This train of deltas by the Poisson summation formula goes to this in the time domain. Convolution gets turned into multiplication right here in the time domain. So this is that train of deltas times that, which produces your set of samples. And multiplication gets turned into convolution in the time domain. And of course, the Fourier transform of chi is a sinc function. Boom, there you go. Or as I like to put it in cartoon form, what's going on here? Here's my signal. Here is the Fourier transform. It's compactly supported. Here's my window. I then use a train of deltas and expand this in a Fourier series. Here's my chi function, transform back. And here's the sample values of the function. And here's the unique analytic spline convolution with the sinc function filling back in the function. And you think, oh, this stuff is great. I mean, are people using it? Well, if we look in the literature, we'll see this person noted with patents in which this person has figured out new ways to do this. It's so-called, I don't know, I didn't put a number on it, but this is the mathematics of the NG network and how to do sampling for it. And when you get a patent, it's a fancy-looking document, which I would not recommend any of the students reading. What you do is you submit your document to a patent lawyer, and they turn it into legalese. And it's like, oh my gosh. I mean, that was so simple when it was math. And I mean, I can read this thing, and even I don't understand it. So that's what patents look like. And believe me, they go on and on and on. Okay. Deconvolution. So I said it'd be fantastic if we could come out with a way to extract information that's remotely sensed. So the first part of the talk, I've talked about how signals can be captured and sent and transmitted. The second part of the talk, I'm going to talk about how we can extract signals and information from things that are remotely sensed. Remember, the convolution integral gives us that. Okay, so here is a beautiful picture, which I apologize, I found from one of my old papers. Thank goodness for the government, man. They publish everything and they store it. I couldn't find this picture anywhere in my notes on yesterday when I was putting together the talk, but hey, the government had it. And I apologize, I don't have Adobe Acrobat Pro to clean this up, but here's where the magic begins. I am going to take as my original targeted signal this double weld formula. Basically what I did was I put together two Gaussians and I say, can you see that this actually has a well in it? And what I'm going to do is do a convolution with this double weld thing with two different characteristic functions. You think, oh, well, they're not very tall and skinny, so they're not the Dirac delta, and certainly he's not going to be able to see into the well. And sure enough, you're right. Okay, so this I'll call mu1, the convolver, and this is what I see when I convolve with mu1. So that I know that there's something going on here, but I can't actually see down into the well. And then I have a second convolver, and look at this number. Why the heck did I choose the square root of 2? Maybe there's some kind of notion of relatively prime or coprime. And maybe one should look to number theory for inspiration. But when I convolve with that, I see a similar kind of picture, but it's more spread out. So I know that there's something going on in the middle of this function, but I don't know what it is. So then my goal is to do some magic here, come up with these things called deconvolvers, so that I can take this whole box from this information and take all this whole box and turn it into the perfect convolver, the Dirac delta in some sense. And lo and behold, what comes out, and this is a older computation. I have a much cleaner computation to see in a second. Wow, I can see down into the well. So that is counterintuitive. Like, what is it so special about the square root of 2 that allows me to see down into the well? And of course, one should look at number theory. In fact, one should get a hold of an ancient Chinese manuscript, and this is a shout out to the Tools of Scientific Computing. So yes, you are allowed to laugh, TSC, because they saw this computation so many times in class. This is from Master Sun's mathematical manual. And we want to solve two modular equations. X is congruent to 1 mod 3, and X is congruent to 2 mod 5. Well, can we come up with a number? And can we come up with it in a systematic way? The key thing is what I'll call the Bezout equation. I'm going to assume that the GCD of these moduli, the greatest common divisor of these moduli, is 1. Another way to say that, an old-fashioned way, is coprime, that M1 and M2 don't share any common prime factors. And if GCD of M1 and M2 are coprime, then I can write down this Bezout equation, which I should think of as a framework. So I'll take the second moduli, 5, and now here is the key insight. I would like to solve for the inverse of M2, but in terms of the first modulus. So the inverse of M2 in terms of the first modulus. So I'm kind of looking at the other modulus to give me that piece of information. And then I take the first modulus, and now I look at the inverse of M1 in terms of M2, and I want that to equal 1. So then back to our equation. I'm going to multiply through by the coefficient A1, and I'm going to mod out by M1. Well, A1 in this case is 1, M1 is 3, but notice when I mod out by M1, this part is 0. This part, remember, this is the inverse of M2 in terms of M1. This is 1. And then I'm going to take that second coefficient and put it in there. And then mod out by M2. In this case, this part is 0, and this part is 1. Okay, let's go back to Masterson's problem. The inverse, and you could do this using the Euclidean algorithm, but we'll just do it, we'll eyeball it, because we're smart. We can count up to 5, I think. At least you can, and I try to do it on good days. But the inverse of 3 mod 5 is going to be 2. And serendipity has it that the inverse of 5 mod 3, well, 2 times 5 is 10, that's also going to be 2. So now let's plug it into the Bezout equation. X is congruent to 1, the coefficient, 5, the modulus M2, times the inverse of mod 3. And 2 is the coefficient, 3 is the modulus, and again, the inverse in terms of the other modulus. And I got 22 mod 5, and of course, that cleans up to X equals 7 mod 15. And we notice that 7 works for both of these equations. Continuance. Again, a shout out to Tools of Scientific Computing. We studied a number known to the ancient Greeks called the golden mean. And it had many wonderful properties, but in particular, it has this wonderful thing called a continued fraction expansion, which is always just 1 plus 1 over 1 plus 1 over 1. And that made it super special. A real number alpha that is poorly approximated by rationals, provided there exists a constant c greater than 0 and n element n, such that alpha minus P over Q in absolute value is greater than or equal to C over Q to the negative n. In fact, if you own a copy of Hardy and Wright or know your number theory, the golden mean is the worst approximate, most poorly approximated by rationals. More number theory language. I wonder how this is going to relate to harmonic analysis. And not all irrationals are poorly approximated by rationals. For example, this number L, sigma k equals 1 to infinity of 1 over 10 to the k factorial, has lots of gaps in it, is an example of what we call a Liouville number. And that's not poorly approximated by rationals, but it is irrational. Liouville invented these to come up with transcendental numbers that he can construct, so he can construct infinitely many examples of. And Liouville is the same guy from the Liouville theorem in complex analysis and Liouville series in dynamical systems. Fantastic mathematician. All right, back to deconvolution. Well, looks like maybe a natural tool is our wonderful friend, the Fourier transform. If f is compactly supported, then it turns out that f hat satisfies a relationship called the Paley-Wiener the Paley-Wiener growth bound. Basically, it's an entire function with a restricted growth bound, and moreover, that analytic function on the real line can be analytically continued to the entire complex plane, and that analytic continuation gives us something called the Fourier Laplace transform. And what's beautiful is now I can bring in machinery from complex analysis. So let's consider a convolution equation where I'm going to assume that mu hat is something compactly supported, like, for example, the characteristic function of an interval. So S equals F convolved with mu. And what I want to do is I want to, given S and given mu, reconstruct what F is. So given S and given mu, reconstruct what the original signal was. Well, we have a little bit of a problem here. If mu is compactly supported, its transform is going to have zeros. And at that points at which you have zeros in mu hat, any transform function that has support at those points is going to disappear. Well, as we saw in our original chart, things like sines and cosines are examples of that. In fact, if mu hat has a zero set, which we'll call z of mu, and I can represent it as eta plus I omega in the complex plane, then all of these functions, g and h, are disappeared. They're wiped out by convolution. And in fact, moreover, since convolution is linear, all linear combinations of these functions are eliminated. So convolution is great, but maybe it's not recovering all the information. But you saw in the picture, somehow we did see down into the well. Well, time for another cheap trick, which will soon become a valuable technique. We take a step back, we take inspiration from the Bezout equation, and we circumvent the ill-posedness by taking several looks at the function. We create a so-called multi-channel system. We take several looks at the function, and we align it so that our sensors, the mu's, their Fourier Laplace transform, do not share any common zeros. Moreover, we make sure that those zeros, those non-common zeros, the zeros in between, do not bunch up too quickly. And that's where the poorly approximated by rationals plays a role. But Professor Hormander, Fields medalist, gave us kind of the first theorem of how to think about that. For the compactly supported distributions, mu generalized functions on R, there exist compactly supported distributions nu. These are the convolvers. These are the things that gather the data. These are the things that are going to allow us to recover. Notice what I'm doing is I'm taking these guys and I'm hitting each one of these with a mu I with a nu I. I'm summing them up. Oh, and I'm recreating the perfect convolution identity element. And this is true if and only if there exist positive constants a and b and positive integers n such that the L2 envelope of the mu I in the transform domain is this very interesting bound. Well, this is basically, as soon as I saw this, I was like, oh, that's just 1 over the Paley-Wiener growth bound, the Paley-Wiener-Schwarz growth bound, because you want to extend it to the sets of distributions. It's like, oh, fantastic. This really makes sense. Hormonder's theorem is an existence theorem, giving the criteria in which we could create a system in which I can recover. And a set of convolvers that satisfy the inequality of the theorem, again, borrowing from number theory language, is said to be strongly coprime. And the nuclei, as I've called them, I got to give them a name. They are, well, again, a shout out to TSC. It's kind of like encryption, decryption that we've been doing, RSA encoding. Those are the deconvolvers. They're going to undo convolution. And what we do is we overdetermine the original signal by a system where we take several looks at it, but we guarantee that the Fourier Laplace transform of these convolvers don't share any common zero. And the problem for solving F is then well posed if the set of convolvers is what we call strongly coprime. This condition gives a lower bound on the L2 envelope of the mu I hats, which guarantees, among other things, that the mu I have no common zeros. Well, look at the characteristic functions that we started with. Characteristic function from -1 to 1 that has zeros basically at the at multiples of pi. Characteristic function from negative square root of 2 to square root of 2, that's going to have zero. Excuse me. The first one's going to have zeros at the integers. The second one's going to have zeros at basically multiples of the square root of 2. Square root of 2 and 1 never match up. They're coprime, if you will. How does this tie in with the Bezout equation? So I take that equation from the Hormonder paper. I take its Fourier Laplace transform. Notice convolution now becomes multiplication. These mu sub i's share no common zeros. And now I apply the machinery of the Bezout equation from number theory. But this is in terms of analytic functions. We solve for a set of deconvolvers which satisfy this relationship. Taking inverse transforms of both sides gives us, the perfect convolver. So this in turn, remember the output of my system is I've taken a snapshot S1, which is the original signal convolved with S1, and then I convolve that with new one. And here I've taken the original signal Sn, I've convolved it with mu n, and now I convolve that with nu n, the undoing convolver. Remember I said if everything's compactly supported, then I can have associativity. So I take advantage of that. I rewrite the relationship in terms of this associativity. This is an F for each one of the convolution elements. By linearity of convolution, I can factor that out. Notice what I've constructed here is the perfect deconvolver. And so that's F convolve with a Dirac delta, and boom, that gives you back F. And you think, wow, does this actually work? Well, in theory, there is no difference between theory and practice. But in practice, there is. Well, it turns out that this actually is also numerically stable, as we'll see in a second. These methods are both linear, convolution with deconvolvers, and realizable. The support of the deconvolvers being contained in the bounded support of the kernels. And so deconvolution at a point only depends on the data near T. I don't need a full knowledge of the thing. I can let my signal come into the system, and I can construct it all locally. And the creation of these sets requires, these coprime sets in the mu's require some manipulation of the decay of the function and the zeros of in the transform domain. And I can't emphasize this statement enough. The tricks for these manipulations come, once again, from the inspiration we got from number theory. Cubes in RD, Peters and Meisterson. Well, if I take characteristic functions of intervals, I will have a strongly coprime system if Ri divided by Rj, those are the widths of my intervals, is, oh, look at this language, poorly approximated by rationals whenever I is not equal to j. That allows me to solve the Hormander equation and then allows me to create a strongly coprime system. I have a theorem, recent paper that's going to appear soon, where I did this for so-called box splines. I took strongly coprime systems and I created spline functions by doing convolution of the boxes. And again, the condition is poorly approximated by rationals. Professor Berenstein and Professor Yeager did something even more brilliant. They did this in radial domains. So a strongly coprime system, if you think of the sensor gathering as being the characteristic function of a disk, and you're sliding that across the disk. By the way, an application of this is I have several letters from the people who make computer chips thanking me for the paper. It's too late for me to get a patent on it. Thanking me for the paper. They use this to test whether computer chips are perfectly smooth before they start cutting things up and making chips. Look at this beautiful result. You have a strongly coprime system if the disks of radius R1 and R2, it's not going to be what you think. You want R1 and R2 to be rationally related, and it turns out that all the quote-unquote coprime behavior is built into the zeros of the Bessel functions. And this is a new area of research, and I'm working on this, and believe me, working with Bessel functions will keep you honest. That's the best way I could put it. So Hormander's theorem gives us the necessary conditions. What I then did was I created the system, but rather than constructing the delta, I created an approximate delta. So I solved what I'll call a modified Bezout equation, where this was basically an approximation of the delta. And then I let the convolvers be these convolve with this approximate identity. And by creating this all with a parameter and letting the support of the approximate identity go down to 0, I actually reconstructed F. And then to solve this, I used complex analysis. So, for example, if I start out with a system -1, 1, chi of that function, and negative, say, the square root of 2 and square root of 2, I can construct deconvolvers, interpolate on this via these formulae. And these formulae look, oh my gosh, how did you think of that? Well, what I did was I went back to the Bezout equation, and I thought, how would I do this in terms of number theory? Well, I looked at z sub I be the zeros of the mu hat sub I, and these were simple zeros. So when z is in the zero set of the first mu I, mu 2 is just the approximate identity function divided by mu hat of t. Notice this is mu 2. It's just like the Bezout equation. These are the zeros of z1. For the zeros of z2, now I solve for mu 1. Then it turns out that I can then use a trick from complex analysis. I took the Cauchy integral formula. I wrote it as multiplying it by 1, but this is a trick Professor Berenstein taught me called the Jacobi interpolation formula. Turns out that this first part of the formula I can solve using the Cauchy residue calculus. This second part of the formula is a remainder term. And I noted that when z is in z1 or z is in z2, mu1 hat times z times mu 2 hat is 0, but the derivative wasn't equal to 0. And so this function had what's called simple poles. I then used complex analysis to solve the Cauchy residue theorem for the Bezout equation. And then I came up with this formula. And notice how beautiful this formula is. The mu1 hat deconvolver is expressed in terms of the zeros of Z2. And the mu2 hat deconvolver is expressed in terms of the zeros of Z1, just like the Bezout equation. Moreover, the strongly coprime condition and plus the support of the approximate identity gave me that 2 went to 0 as n goes to infinity. And so you think, wow, it's a lot of math. Does this actually work? Let's take a look at some pictures. Here's what a deconvolver looks like. Highly oscillatory. And then you notice, since this is the deconvolver associated with the square root of 2, notice it's 0 outside of negative root 2, positive root 2. Here's the deconvolver for the second one, but it's expressed in terms of the zeros of Z1. Notice the deconvolver has support from negative 1 to 1. Again, expressing like the Bezout equation, the duality of reconstructing the formulae. What I'm going to do is take the deconvolver and multiply it, do a convolution with the approximate identity and the first convolver, and I get this formula. Here's the second deconvolver, and I multiply that by mu2, and there's my approximate identity. Here I created an approximate identity, used a C infinity function that gave me a lot of extra decay. So I knew in theory that this was going to converge. And look at the beautiful equation that I got out, the beautiful result that I got out from this. I knew that I had it as soon as I got this picture. There it is, the Dirac delta with a little bit of noise. And I thought if Professor Bukovalis and Professor Robinson attended, I would throw in that, yes, I'm a good engineer and I computed log of spec m. And there it is. And that shows you, wow, this is really close to the Dirac delta. So you think, oh, well, what about that double weld problem that I started with? Well, here's what the output of the one channel is. Here's what the output of the other channel is. I'm going to hit this with the first deconvolver, this with the second deconvolver, add them together, and lo and behold, what you see here is the original function in the dash and the output function in the solid. And yes, even though I'm using larger convolvers to reconstruct, I can see down into the well. Amazing. Deconvolution. It actually works. Well, I have a few minutes left, and so I'll quickly go back to the sampling formula and show you how one could use that Jacobi technique to solve for the Shannon sampling formula. So remember, the first time I proved it, I used the Poisson summation formula. So here, I want to be consistent with the thesis of my talk and go back to that beautiful quote of Bachner. I need to now show you how the Cauchy integral formula could also give us this. This is the bound that I talked about. This is the Paley-Wiener growth bound. And it basically says you have an analytic function, and moreover, you have a control over the growth of the function. Well, what I did was, to make things simple, I chose a sampling rate which was simple so that I could use a particularly simple function to do the reconstruction. And I chose contours, so I avoided the zeros, and then I rebuilt the original function. So here's my signal. It's an analytic function. I write down the Cauchy integral formula. Here is the first part of the Jacobi interpolation formula. Here's the remainder part. S is the part that I do the sampling formula on. R is the part that I do the remainder, to estimate the remainder. And what I found as a byproduct of this was an engineering result, which was in the folklore, that if engineers are always oversampling the signals. I was like, why do you do that? Why not just sample at Nyquist? He goes, oh, because it makes everything work so nicely. What they didn't tell me was something I had to figure out on my own, was that that remainder term dies exponentially if I oversample, even by a slight amount. But that if I sample exactly at Nyquist, all I get is like polynomial decay. And I'm like, oh, why didn't you just say that? It's like, well, we didn't know that. I mean, like, I showed one of my friends, Brian, this equation. He's like, oh, that's cool. That's how it works. It's always good to talk to the engineers. Anyway, I need a little trick. I'm going to take the sine function and do an expansion of it in the Weierstrass product representation. And the other trick I need is a generalization of partial fractions that goes back to Mittag-Leffler. So let's see if I can combine these things and make the sampling formula. Well, I'm going to let Rm be estimated later. Or actually, I did that earlier, and I showed you how quickly it decays. So I'm just going to work with the first part of the Jacobi interpolation formula. Here's the formula. My integral is with respect to zeta. So I now can rewrite this in terms of remember this is a sine function, so I can write it in terms of the Mittag-Leffler expansion. The Weierstrass approximation. Then I rewrite this part in terms of the Mittag-Leffler expansion. That gives me a sum and an integral. I can invert the sum and the integral because this is a finite sum. Moreover, this converges uniformly on compact subsets. So even if I yank the limit early, I can still do that switch. So 1, 2, 3, 4. I'm at this point. I then evaluate the Cauchy residue calculus. It gives me, oh my goodness, it gives me back the original sample function Fn at the points plus this formula S prime of n, but that's just the sine function. This then is sine of pi z times here's your sample values. There's your sinc function at the points plus the remainder, and there is the formula. 1 is Jacobi interpolation, 2 is Weierstrass approximation, 3 Mittag-Leffler, 4 linearity, 5 Cauchy residue calculus, 6 Weierstrass, and 7 the sinc function. Since Rm goes to 0, as m goes to infinity, we get sampling. And at this point, I will say thank you very much. We got started a little late, but I think I've given a sufficient amount of information for now. So,
Thank you, Steve. Let's
all
thank
right.
Professor Casey, and let's see if we have any questions. Questions? No questions? Anybody?
Hi, Dr. Casey. I have a question.
Yeah.
Can you talk more about those sampling formulas and how they're derived?
Gladly. Let me go over here. This is in a big paper. Remember that technique that I derived? This is the paper. Remember that technique I derived the sampling formula. So let me show you a beautiful trick which goes to an engineer called Papoulis. Here's a Shannon sampling theorem where I have sampling at Nyquist. There's my sinc function. There is the perfect reconstruction of the function.
Dr. Casey,
Yeah.
do you want to share your screen?
And of course, thank you, Darcy. You always are good at that. And here I now will share the screen. Okay, wait a second. Share. I need to Pick the wrong thing. And there we are. That's what to share. Ah, good. Well, I use that interpolation formula to give us, here's that general setup. Here's the sinc function that I just went through. Here's the Mittag-Leffler expansion. Here's what the residue is. And then you'll notice there's what I had to present in Beamer on several slides. But Papoulis came up with this great idea that we could sample at a slower rate, but at each point, we need more information. So we could actually reconstruct the function exactly as long as I had both f and the value of the derivative at that point. And notice now it's the sinc function squared. So I'm wondering, did my machinery work on this? Well, my generating function, sampling generating function, is sine squared by z over z. So here again is the Jacobi interpolation formula. I chose my contours carefully, so everything worked. Once again, the Weierstrass approximation. Here, my Mittag-Leffler expansion was a little more complicated, and it took me, this took me like an afternoon to work this out, and I double-checked it, and I went with Professor Balan at Maryland and Professor Benedetto, and sure enough, they gave it the blessing, and it works. And now look at this beautiful machine. I sample at half the rate, but with twice the information, this being sinc squared. I then do the Mittag-Leffler, first the Weierstrass approximation, and then the Mittag-Leffler expansion. It's more complicated. I get out these as my formula in the Mittag-Leffler. I then did the Cauchy residue calculus on each one of these. Notice, bam, I got the derivative. And each one of these is now a perfect reconstruction formula. And now I have 4 pi sine squared out front, and then a perfect reconstruction, and boom, there is the Poisson formula. But what I also noticed was, wait a second, something's going on here. The result generalizes. I use the Jacobi interpolation formula, where now I sampled at a kth of the rate, but used sine raised to the k. And when k is 1, I got the sampling formula. When k is 2, I got the Papoulis generalized sampling formula. And for general n, in one shot using that machine, I got the Papoulis generalized sampling. And that got me to thinking, being complex analysts, something's going on here. It's like we're taking the signal information and we're encoding it at each point. We're using only half the points, or a third of the points, or a fourth of the points. But at each point, we're requiring twice the amount of information, or 3 times the amount of information, or 4 times the amount of information. Wait a second, that sounds like complex analysis. If you have infinite knowledge of a function, which is analytic, at a single point, you have its Taylor expansion. So what was interesting is I derived a way through sampling to think about the Taylor expansion. And I was talking about this with a really good friend of mine. She's a professor at the Weizmann Institute. Her name's Yanina Eldar. And she said, yeah, I mean, that's great. Like, look at my book. I started a discussion on this. So Yanina and I have plans to write this up as a paper. It's fantastic because here you create in one machine all these different formulas. So, excellent question. And I think I'll stop the share and.
Very cool. Thank you.
And I'm hoping I appeal to the number theorists out there that the use of the Bezout equation And again, a shout out to my students in Tools of Scientific Computing, because we solved those equations. I was like, how am I going to explain the analytic Bezout equation? And then we solved that equation, and it's like, oh, that's perfect. That it is, in fact, that whole language in terms of that simple little equation that I solved at the beginning. So.
Oh, very cool. Anything else we have? Any other questions? I'm gonna take a silence as no.
Yep.
All right, everyone, let's thank you, Professor Casey, again. And if you happen to come up with the question, you can always email, I suppose, or catch him in a hallway.
Right. Meet me in the hallway and we can work on Bessel functions.
Yay.
Yes.